Now, with domain and range, we're going to look at a couple of different forms, or domain and range in a couple of different settings. Our first one would be domain and range of discrete data. And this one's kind of the easiest. It's really cut and dry. Now, when you have domain and range of discrete data, we talked about discrete data is tables, mappings, scatter plots, etc. Things that are the dots are not connected. We are just going to list all of our possible values. That's going to look something like these, where it's the variable you are defining followed by the list of numbers that it is equal to. Now, notice when you write those lists, we put them in curly brackets. That's just to show that it's a set together. So if we looked at each of these, for our very first one, we'd set it up. We'd say, okay, X, you're going to either use a colon or a bar, either way, just to show that, hey, X is everything following it. And we list our X values, -2, -1, 0, 1, and 2. We can clearly see these X values in our table. We're going to do the same thing for range, except we remember that range is Y. So we'll set this up as Y. And we're going to list our Y values. Now, it is a best practice to order the values from least to greatest. It is not required, but typically you will see it given to you from least to greatest. So I'm going to do that here. I'm going to start off with the least value. And I'm going to list my Y values from least to greatest. So we now have our set of Y values. Now, when reading domain and range, this does not mean that you have the point -2, 1. This simply means that there is a point where the value of X is -2, and there is a point where the value of Y is 1. Those don't necessarily correspond. You're just listing that type of value. Take a second. Go ahead. I want you to try to list the value of domain or the domain and range values of our second one, of that scatter plot. All right. We would then check your work. We'd say the domain of X, the X value of this blue dot is 2. The X value of this green dot is 3. The X value of this purple is 5. Black is 7. Our reddish orange color is 9. Now, notice when I was looking at domain and range right here, I went from left to right. When pulling it from a graph, your smallest domain value is the furthest left. Your largest domain value is the furthest, that's totally misspelled, right. And that's going to be something to keep in mind for later. So then we're going to go ahead, we're going to do the same thing with our Y. You've already done the same thing with your Y, except instead of left to right, to go from lowest to highest, your lowest Y values are on the bottom. So we would go from bottom, which here's our lowest y value at 1, and we'd keep listing them until we got to the top. So we're going to have from 1, our red y value is 3, our green is 4, our black is 5, and our purple is 6. So we've listed our y values. Finally, you should be able to put the domain and range of this mapping. We have 10, 20, 30, 40, and our range is 15, 25, 35, 45. Our second situation we would be looking at domain and range for is when there is continuous data. From last class, we should remember continuous is basically when it's all connected. This would be lines, segments, curves, equations. Today, we're primarily just going to look at those graph settings. Now, when writing your domain and range for a continuous set of data, you're going to use that inequality notation. Hopefully, your opener kind of got you back into the habit of thinking about that inequality notation. But remember, when writing an inequality, you're going to start off with an idea. You want to say it's from some number to some number. And today we're going to practice writing this out before we convert it to an actual inequality. Same thing when you get to the range. We're going to say it's from a number to a number. Then we're going to convert to an inequality. Now, you'll see these two formattings are both at the top of your page, but when writing an inequality, it is generally from that smallest value. You use one of your inequality symbols, x, which is less than or equal to your largest value. Now, because domain is the x-axis, the x-axis. The x-axis is the horizontal, which runs from left to right. So in identifying your bounds of the domain, we're going to remember that domain is from left to right. And range, because the y-axis, actually gonna get rid of this word inequality because I need some more space. The y-axis is vertical. Which means when looking for the smallest y value, we're actually going from bottom to top. And the reason I say bottom to top and not top to bottom is because remember, we always want to arrange these from smallest to largest. Our best practice is from smallest to largest. So let's try it. Our domain here, we would look closely. I'm going to zoom in. When I made these, I didn't realize quite how hard it was to see those graphs. But when we said domain, I said the important thing to remember is domain is from left to right. So we want the furthest point to the left. Well, if we look on our graph, we could follow the whole graph moving left. Oh, this is our furthest point to the left. This is the one we want to keep here. Well, that point is at -1. So we know we're from -1 to, we're going to do the same thing. If we got on our graph and we followed it all the way to the right, it's going to stop right here, which we have a x value of 2 here. So our graph would be from -1 to 2. And if you can write this simple word phrase, that's half of our battle. Because now we can turn that into an inequality. We put the smallest number. We set up with less than x, which is less than 2. Notice we always use less thans because we're smallest to largest. Always are using less thans because it's smallest to largest. Now, we do need to consider, are either of those going to be equal to? And to do that, we would look at the points on our actual graph. So, right here, we are looking at, actually, let me change the color to be different from the graph. Right here, we're looking at a closed circle, which is where our value is 2. So our inequality needs to show that as well. It needs to be included. This should be a less than or equal to. The other end is an open circle. So at -1, it is excluded, meaning it's just less than, no equal to. So with that, we have our domain. We should be able to write it out down at the bottom. -1 is less than x, which is less than or equal to 2. So in doing our range, we're going to start with the same thing. We're going to say, well, range is not left to right, but bottom to top. When looking for that range, I'm going to follow my graph. Where's that lowest point? Oh, we've made it to our lowest point. Here, the y value is 0. So from the bottom, our lowest value is 0, 2. If we follow our graph again, we're going to follow it up. We want to go to the highest point. Oh, notice the highest point is not necessarily an endpoint. The highest point of our graph right here is in the curve. And the value of y would be 4. Now, notice, if we're looking at that point right there, is there a specific point? No, we don't see an endpoint, not like we do here. So instead, we have to know that this is a closed circle. If you think about it in terms of numbers, if I tell you the number 8, is it positive or negative? You should think to yourself, hey, 8's positive. How did you know? Because it's not negative. All right? We don't have to write a plus in front of a number to know that it's positive. It's understood. Just like that, if there is no open circle, then it is understood that it is a closed circle or a closed point. That is on the graph. It is a closed point unless it has that distinct open circle. So here we'd go from 0 to our highest value is 4. We're going to need to write our inequality now. So we would say, set it up, 0, our y values, and our 4. We always are using less than. Now we need to consider, are these equal to? Are these included? Well, our point at 0 is obviously included, so we're going to make it or equal to. Our point at 4 is not an open circle, so we're also going to make it or equal to, which gives us our range. 0 is less than x, excuse me, whoa, major mistake there. 0 is less than or equal to y, which is less than or equal to 4. Now, that mistake I just made, that is a common mistake. Be careful. Domain is always x, range is always y, because those are the set of values that you're interpreting. If we do the same thing with our next graph, remember, domain is left to right. What is our furthest value left? What is our furthest value right? So if I look here, I'm going to follow the graph to the left. All right, well, my value is -4. 2, I'm going to do the same thing. I'm going to follow my graph to the right. My value is +3. So my domain is -4 to +3. I'm going to write that as an inequality. Let's go ahead and set it up. -4 is less than x, which is less than 3. Your x is always in the middle. You're going from least to greatest, and you use less than sign. Now we need to consider, do either of these inequalities need to be equal to? Well, our point at -4 is a closed circle, so it would be equal to, whereas our point at 3 is an open circle. So we have our compound inequality that just says, hey, x is all of the numbers between -4 and 3. We're going to do the same thing with range. And for range, we say bottom to top. So our lowest y value, we go and we put our pin on the lowest point. It would be right here. I want you to notice though that this value isn't at -1 and it's not 0. It's in between. So we would estimate that. I would probably say it's about -0.5 or -0.5. 2, we're going to take our pin and go put it on our highest point. Our value of y right here is 3. So we would have from -0.5 to 3. We're going to set up our range. Our smallest value is less than y, which is less than 3. Always less than. We need to consider, do either of them need an open circle? Well, or excuse me, do either of them need a line under it because of a closed circle? -0.5 has an open circle, so it's good, but 3 has a closed circle. So we should have -0.5 is less than y, which is less than or equal to 3. Now, before we move on to our next section, I want you to try it. Obviously, I want you to go ahead and just do this on your whiteboard, on your notes. In class, if I was there, we would have held up our whiteboard so I could do a quick check. Here, we want to say, okay, domain, left to right. So first thing, I'm going to have that idea, and I'm just going to say number to number. My furthest point to the left is -6. My furthest point to the right is 2. So this is my thinking box. I don't know why I wrote curly brackets. It doesn't really matter. So -6 to 2. My domain needs to show that x falls between -6 and 2. Now that I've written it, I'm going to go back and look. These are both open circles. Which tells us that if you're at those values, they are not equal to. We're going to do the same thing for range, except range is bottom to top. Let's list our numbers. If we're looking at our graph and we put our pin on it, the lowest value is right here. So -10.8. 2, we go put our pin on it, our highest value is not at the end point. It's actually above it. Here's our highest value. So the value of y at this point is 0. So we know our top would be to 0. We're going to set up our inequality. Smallest number less than y less than largest number. We need to consider, are either of these equal to? Well, this has an open circle. This is part of the graph itself. If it's on the graph and it's not a clear open circle, we know that it is equal to. It is understood to be equal. All right. Hopefully that helps you with writing those inequalities and linked back to that extra practice we got with Unit 3 and writing the inequalities in your opener. Domain and range of continuous graphs also has some special cases because your domain and range can continue forever in one or both directions. If we think about this on a graph, that's going to be used or shown using an arrow. If you sketch a graph, well, if it's got an arrow on one end, we know that it keeps going and going and going and going, even when it's off the page, even when those values don't exist. Or excuse me, don't exist on your graph. They exist because infinity. All right. So we have to think about what that arrow means. When does it stop? And in these cases, we may have a special case or special case solution known as all real numbers. And what all real numbers is telling us is it's similar to IMS. It is from negative infinity to positive infinity. Every whole number, decimal, fraction, irrational, or rational number. So it's literally all of the numbers, negative infinity to positive infinity, all real numbers. You'll often see it denoted with this funky looking R, in which case you just draw a regular R and put a bar on the back of it, and that means all real numbers. I would accept ARN or writing all reals, as long as you show you know you're talking about all of the numbers. Now, let's try a couple of these. If we look at our first graph, we're still going to ask ourselves the same question. For domain, we're thinking, okay, from left to right. Let's get those numbers. Now, if we take our pen and we put it on the furthest point to the left, our x value right here is 1. So we know if we have from 1, 2, we then take our pen and we put it on the furthest right, except we see that the furthest point to the right, either one of them, isn't a point, it's an arrow. So what that means is it keeps going and going and going. And although, yes, this one is getting lower as it goes, it's continuing out. It's going to continue on in that outward direction forever. So we would say from 1 to infinity, because it's going to infinity. Now, when we write our compound inequality using that, I'm going to zoom in on this, I'm sorry. Using that infinity, we would set this up same as usual, 1 less than x less than infinity. When you write infinity, though, we can go ahead and just erase that. You're not actually going to write out the infinity. For me, it's helpful to write it out and then erase it. That way you know you've got the rest of your inequality set up correctly. We do need to check to see if our inequality needs to be or equal to. This is on the graph itself, which tells us this should be equal to. It is included. It is included. So all this statement is saying, you could write it the other direction, is x is all of your numbers greater than or equal to 1. It's all of your numbers above 1. So our domain is all of your numbers greater than or equal to 1. We're going to use our same idea with range. Except remember, range is we're going bottom to top. If we consider the bottom here, and we put our pin on it, oh, it's an arrow again. It's not a point. Also, this arrow continually goes down. It's going to keep going down forever. So our bottom, it's going on forever, and it's going down forever. We call that negative infinity because it is down. It's the negative numbers. So we'd say negative infinity, 2. Do the same thing for going up. Our highest point is also an arrow. It's going to keep going to infinity. Here we just say infinity because it is positive. So from negative infinity to positive infinity. We just talked about that we would call that all real numbers. Now that we've looked at this first one, let's go ahead and you try the second one. Think about, for domain, left to right, and for range, bottom to top. If it helps, practice doing that each time. Write that number phrase. So domain, we would look at it. We're going furthest to the left, which would be right here. It's an arrow. It's going to keep going out forever and ever and ever. So we would call that negative infinity because it is the negative x values. 2, we got an arrow. It's going to keep going out forever and ever and ever. So this is positive infinity. From negative to infinity to positive infinity, we call all reals. We're going to approach our range and we're going bottom to top. Our lowest point would be right here at this turning point. Well, the x value at this turning point would be 0. So our bottom would be 0, 2. We look again at our top. Our highest point is an arrow, which tells us that it keeps going up and up and up to infinity and beyond. So we have 0 to infinity. We would set our inequality up. 0 is less than y, which is less than infinity. We know that 0 is on the graph, so that is equal to. And we remember, hey, we don't actually write that less than infinity. It's understood. It's given. So we would say 0 is less than or equal to y. Or you could write that single inequality statement as y is greater than or equal to 0. Lastly, we're going to do the same thing. Domain. Left to right. When going left, we look to our furthest point. We notice it's an arrow, so that's going to give us infinity. This is negative infinity. Our furthest point to the right is also an arrow. It's going to the positives though. So we have negative infinity to positive infinity. Infinity to infinity tells us all reals. We do the same thing with our range. With range, we're going to say bottom to top. Here we would have it going down forever, so that would be negative infinity. 2 going up forever, that would be positive infinity. So here we would have all real numbers. Our last domain and range situation to consider is domain and range in the real world. And this is because of real world constraints or reality. We have to think about this realistically. For example, if your domain or your x-axis represents time, we would have some constraints on that x-axis, being that time cannot be negative. You cannot have a negative time. You cannot go back in time. So based off of that, we know that our domain is everything greater than or equal to 0. Now, it could also have an endpoint, but our absolute smallest value when you have time would be 0 because you can't go negative. Money could be controlled by how much you have. Let's say you have $25. You're at school. Whoops. You've got $25. You want to go to the break store. Could you spend $25? Yes. Do you have to spend $25? No. You can spend $5. You can spend $2. You can spend $0. So here, our domain would be from 0 to 25. Well, let's say that the items at the break store cost $3 each. Well, the number of items you can buy is controlled by how much money you have. They cost $3 each. You could buy no items, or you could buy, how many $3 items can you buy in $25? 6 items. Now, this has an additional constraint. It's all integers. Remember, an integer is a whole number. The reason it's all integers because you can spend part of a dollar. So this would be all numbers between 0 and 25. But you can't buy part of an item. So you can only buy 0, 1, 2, 3, 4, 5, or 6 items from the break store. That's why it is the integers. You can't buy 5.5 items. You can't buy 5.7. Got to buy a whole item. So 0 to 6. It would have to be 6 because 7 items wouldn't be under $25. 7 items would cost $28. So using that knowledge, let's take a look at this scenario where we have Joe. Now, I want to say a couple of things. One, I understand $7 an hour is super cheap. But this would be like, that's how much money he takes home after taxes. Let's say his actual salary is probably $10, $12 an hour. But he only gets to take home $7. It says take home pay. So Joe had a summer job that pays $7 an hour, and he worked between 15 and 35 hours every week. His weekly salary can be modeled by the equation S equals 7H, where S is his weekly salary and H is the number of hours he worked in a week. Describe the domain and range for this problem using appropriate notation. So first thing, let's work on what is the domain in this problem? What is the range? When you start talking about real world scenarios, we need to label which is each. So think about it. If we graphed this, what is the label on our x-axis? What is the label on our y-axis? So here, we would need to think, okay, well, we're talking about two things. We're talking about his, weekly salary and the number of hours he worked. So one would be one axis and one would be the other. Well, how much money he makes, the money he makes depends on the hours, making hours our independent variable. You should remember earlier we talked about independent is x. So we can say domain is our hours and range is our money or salary. So when we talk about domain, what's the least number of hours he works in a week? It says 15 to 35 hours. So we would want to say, all right, we know domain is 15 to 35. Now we use appropriate notation and set up our inequality. So 15 is less than, got to use x, which is less than 35. We need to think about, can we work exactly 15 hours? Yes, so it's equal to. Can we work exactly 35 hours? Yes, so it's equal to. So we now have our domain. We do the same thing for our range. However, we're going to have to do a little bit of math for our range because it didn't tell us our possible paychecks. It just told us how much we earned per an hour. Well, if we worked 15 hours, we'd earn $105. So we know that, so we earn $105. If we work our max 35 hours, we earn $245. So our range, our salary is 105 to 245. We set that up with our Y because range is our Y. I think I did this math right. It could be wrong. Y'all check it with your calculator. I don't have a calculator handy. Now, we need to consider, if I work 15 hours, am I getting paid $105? Yes, exactly. So it's equal to. If I work 35 hours, I'm getting paid exactly $245. It is equal to. Our second question is, what does each value of the ordered pair mean in the context of the problem? So we have 20, comma, 140. Well, 20 is an X value. 140 is a Y value. Because we labeled them, we know X values are hours. Y values is money. So we should have 20 hours earning, because that's what we're doing, we're earning money, $140. Okay. If we take another look or a look at another one, this would be one that might show up on a state test or a benchmark. This is a standardized or even a ACT. I've seen domain and range questions on an ACT. A veterinarian office can schedule up to 3 patients per an hour for each 8-hour workday during each 4-day work week. The function f of x represents the number of patients scheduled each work week, which best describes the domain of the function. So we need to think about what all can be scheduled and what is being represented here. So first thing, what is on our x-axis? What is on f of x? From last class, you should remember that f of x, this means y. F of x is the same thing as y. So, we are talking about the number of patients scheduled each work week. And we want to know the domain. The number of patients would be the domain. So, we don't even need y. If it says domain, you should be able to get rid of y, which means we should get rid of the y answer choices. From there, we would think about, okay, how do I figure out how many patients? Well, you get 3 patients per an hour, and there are 8 hours, so we can multiply that at, and there are 4 days. So 3 times 8 times 4 is 96, which is where they got that 96 from in our answer options. From there, we have to consider our second part. X can be any real number, X can be any whole number. Remember, real numbers are whole, decimal, fraction, all of them, rational, irrational. So 96 patients. Can you have a fraction or a decimal of a patient? No, so it shouldn't be the real numbers. We should have the whole numbers. Again, we could answer another one and try it. So I want you to give this one a try just by yourself. A convenience store clerk earns $11.50 per an hour, or any fraction thereof, and works up to 40 hours per week, which best describes the domain of the function representing the amount of money earned y for working 8 hours in 1 week. So here, H hours is our domain. H is domain. Y is range. So we know the number of hours would be the domain. Well, 460 comes from saying 40 times 1150. So that would still be money. We should get rid of A and B because we're not talking about the money. We're talking about the number of hours. Well, if we look at C and D, our difference is any whole numbers, any real numbers. This key phrase, any fraction thereof, means you can work part of an hour because time is continuous. So it is not just the whole numbers, it is also the real numbers.